Thank you for the kind introduction. My name is Yunpu Zhao, and I'm from Dr. Russ Powers Group in University of Florida. So my topic today is the intermetallic nanoparticles tailored for Parahydrogen enhanced NMR by heterogeneous catalysis. Okay, so the Parahydrogen enhanced NMR achieved by heterogeneous catalysis have been extensively applied in many fields, including the study of reaction mechanism, reaction monitoring, and low-field biomedical imaging. So supported metal nanoparticle is one of the most common kind of catalyst for heterogeneous PENMR. Copio first reported that the alumina-supported platinum nanoparticles can produce hyperpolarized propane gas. Our group also demonstrated that the titanium oxide-supported iridium nanoparticles can be used as a catalyst for heterogeneous PENMR. So the major advantage of using the heterogeneous catalysis is that it provides easy and quick separation between the catalyst and substrate, so that it could generate contaminant-free hyperpolarized substrate for biomedical imaging. However, its application is limited by the lower polarization level and signal enhancement compared to homogeneous catalysis. So more detailed study on monometallic nanoparticles for PNMR has been conducted recently in a study of 3 titanium oxide-supported metal catalysts for propylene PNMR. The rhodium nanoparticles generated 1.3% polarization, while the palladium and platinum catalysts showed much smaller hyperpolarized signal. And later research optimized the synthesis of such catalyst and eventually increased the pairwise selectivity to 7.1%, which corresponds to around 200-fold signal enhancement in Pasadena spectrum. However, this number are still much lower comparing to the PNMR by homogeneous catalysis. So to understand the reason for such a low signal enhancement and further guide the design of new catalyst, it is essential to understand the hydrogenation mechanism on the metal surface. So the hydrogenation of alkene substrate on the metal surface can be described by a horizontal planing mechanism. The parahydrogen will first dissociate on the metal surface, and the unsaturated substrate will also chemisorb on the surface at the same time. Then the hydrogen atom in the vicinity of the substrate will be added onto the carbon double bond in stepwise addition. And finally, the hydrogenation product will desorb from the surface. So one of the key requirements for the polarization transfer from parahydrogen to the hydrogenation product is that the 2 hydrogen atom added onto the carbon double bond must come from the same parahydrogen molecule, which is also referred as pairwise addition, so that the spin correlation of parahydrogen can be preserved. However, the active metal surface provides low energy barrier for hydrogen diffusion, which promotes quick randomization of hydrogen atom on the metal surface and eventually lead to less pairwise addition and low signal enhancement. So usually we use the pairwise selectivity to evaluate the PNMR activity of a catalyst. The pairwise activity is a parameter that describes the ratio of hydrogenation product obtained from pairwise addition. It can be calculated by taking the ratio of experimental enhancement factor to the theoretical values. So inspired by such hydrogenation mechanism, our group demonstrated that the incorporation of a secondary inert metal on the active metal surface can significantly increase the hydrogen diffusion barrier, thus boost the signal enhancement. So we studied the PT-tin intermetallic catalyst with different platinum to tin ratios. The monometallic platinum 111 surface has a low hydrogen diffusion barrier of 6 kilojoules per mole. After incorporation of tin, the diffusion barrier increased to 50 kilojoules per mole on the PT3 tin surface. When we add more tin to such a intermetallic nanoparticles, with a PT to tin ratio decreased to 2:1, the surface hydrogen diffusion barrier is further increased to 100 kilojoules per mole. So accordingly, in the propylene PNMR study, the PT-tin and PT3-tin showed significantly higher Altadena signal comparing to the monometallic platinum catalyst. And the pairwise activity for the PT-tin catalyst is 11.7%, which increased 3,000-fold from the monometallic platinum catalyst which only gives a 0.03% of pairwise selectivity. So besides the PTTN system, we did a catalyst survey on a wide scope of intermetallic catalyst with different composition and supports. And here are the results plotted as a conversion versus pairwise selectivity. So we observed a inverse correlation between conversion and pairwise selectivity as a general trend to most of the catalysts. So among all these catalysts, we found the mesoporous silica-supported rhodium-indium-3 catalyst stick out for its superior pairwise selectivity. So my talk today will focus on a systematic study on the rhodium-indium intermetallic system. So in the synthesis of the rhodium-indium Sb15 supported intermetallic nanoparticles, the mesoporous silica Sb15 was first synthesized by the TOS hydrolysis. Then the rhodium nanoparticles was deposited in the pores of Sb15 by incipient wetness impregnation method. In this process, two different precursors, rhodium chloride or the rhodium alkali-3, are used in the synthesis, and we found that the different rhodium precursors would affect the formation of intermetallic phase, which will be discussed in detail later. And when we once we got the rhodium nanoparticles, we used the same methodology to incorporate the secondary inert metal tin into the rhodium nanoparticles, followed by a 500 Celsius degree reduction. And the rhodium to indium ratio can be varied by controlling the molar ratio of rhodium and indium precursors. So the rhodium-indium phase was confirmed by the XRD spectroscopy. The XRD pattern of rhodium and rhodium-indium catalyst agreed to their standard pattern pretty well. However, in the rhodium-indium-3 catalyst, although the rhodium-indium-3 is the dominating phase, a small amount of rhodium-indium phase impurity was also observed. So the catalyst with different rhodium to indium ratio was studied in propylene NMR experiment. 10 milligrams of each catalyst was packed in a U-tube reactor, and the reaction temperature was kept at 200 Celsius degree. And the surface model of this three catalysts was also constructed in order to better interpret their different PNMR activity. So the rhodium catalyst showed the highest conversion as a comparison to rhodium-indium and rhodium-indium-3. So this can be explained by the rhodium-3 fault hollow sites on the rhodium-111 surface, which is the active site for hydrogen absorption. The other two catalysts only have isolated rhodium atoms on their surface, which inhibits the co-absorption of hydrogen and propylene and lead to a lower conversion. Although the rhodium catalyst produces strong alpha-adeno signal, the pairwise activity is only 0.3% due to its high conversion. The rhodium-indium catalyst showed a low conversion as well as low alpha-adeno signal, yielding a 0.97% of pairwise activity. In contrast, the rhodium-indium-3 catalyst generated the highest alpha-adeno signal despite the low conversion, yielding a remarkable 23.6% pairwise activity, which is the highest observed pairwise selectivity so far for such heterogeneous PNMR experiment. The PNMR results can be interpreted by the calculation of hydrogen diffusion barrier on the catalyst surface. Unlike the PTTN system, the rhodium and rhodium-indium have the same hydrogen diffusion barrier, which contributes to their similar low pairwise selectivity. Although the hydrogen barrier of the rhodium-indium-3 is not calculated, the increase of the hydrogen diffusion barrier on the rhodium lab 2 indicated that with more inert metal being incorporated onto the rhodium surface, the diffusion barrier is further increased, which lead to a higher pairwise selectivity. So we also did a temperature-dependent study on all three catalysts. The conversion of all three catalysts dropped at 300 Celsius degree, which indicated the catalyst deactivation at high temperature. However, for rhodium and rhodium-indium-3 catalyst, the drop of conversion is accompanied with the increase of pairwise selectivity. This indicated that the deactivation is likely due to the coke formation on the surface that blocks the active site for hydrogen absorption and slightly restrict the hydrogen diffusion. In contrast, both conversion and pairwise activity dropped at 300 Celsius for the rhodium-indium-3 catalyst, which is more likely due to the surface reconstruction at high temperature. So despite the remarkable results achieved by the rhodium-indium-3 catalyst, the reproducibility of the synthesis of rhodium-indium-3 nanoparticles remains a challenge. So therefore, we performed a optimization for the synthesis procedure. So as I mentioned before, two different precursors, rhodium chloride and rhodium alkyd, are tested in the synthesis of rhodium-indium-3 nanoparticles. The XRD showed that the rhodium-indium-3 phase is the dominating phase in the rhodium-indium-3 synthesized from rhodium chloride precursor, while the rhodium-indium phase became the dominating phase when the precursor is rhodium alkyd. On the other hand, the TEM showed that the rhodium alkyd precursor produced smaller nanoparticles than the rhodium chloride 3. So this indicates that the rhodium-indium phase is more stable in smaller nanoparticles, which is likely due to the higher formation energy of rhodium-indium-3 phase. And the propylene PNMR study showed a dramatic signal loss when used rhodium alkyd precursor, which corresponds to the lack of rhodium-indium-3 phase. And the slight variation of rhodium to indium ratio around 1:3 could affect the formation of rhodium-indium-3 phase as well. As seen in the XRD, all three catalysts have the mixed rhodium-indium and rhodium-indium-3 phase. The rhodium-indium 3.2 has the highest ratio of rhodium-indium-3 phase. Then is the rhodium-indium 2.8, while the rhodium-indium 3.0 has the least rhodium-indium-3 phase. So the pairwise selectivity obtained from the propylene PNMR study indicated that the more rhodium-indium-3 phase, the higher the pairwise selectivity. So in conclusion, we demonstrated that the intermetallic nanoparticles can significantly increase the signal enhancement and pairwise selectivity by restricting hydrogen diffusion on the metal surface. And we achieved a remarkable 23.6% pairwise selectivity by the rhodium-indium-3 synthesized from rhodium chloride precursor. And the rhodium-indium catalyst deactivates at high temperature due to coke formation and surface reconstruction. And we revealed the precursor effect and the stoichiometry effect of that could affect the formation of rhodium-indium-3 phase. And the reproducibility of the synthesis is still a challenge for us for right now. So we are going to conduct more further study on this. And lastly, the catalyst survey of many other intermetallic catalysts was performed and showed that the conversion and pairwise selectivity are inversely correlated. So with that, I would like to thank my research advisor, Dr. Russ Bowers, and all the Bowers Group members. And I want to give my special thanks to our collaborators, Dr. Wenyu Huang and Minda Chen from Iowa State University for the collaboration on the catalyst synthesis. And also I would like to thank our funding resources. And lastly, I want to advertise our group presentations in the PERM this year. So we will have Dr. William Hale on Wednesday to present our continuous flow setup for the PNMR study. And also we have two poster sessions from Yunpu and Maria Jose Ferrier. Yeah, and that's all. Thank you very much. And I would like to take questions.
Awesome. Thank you, Tommy, for a great talk. I guess one short question we had was there was a small peak at antiphase signal at 4.5 ppm in one of the spectra that you showed. Is that orthohydrogen, I guess, that you're seeing hyperpolarized?
At 4.5 ppm? Oh, you're talking like something like that? I think that is the pairwise replacement that we observed with all the intermetallic catalysts before.
It was a different spectrum, but it's okay.
Boyd, which spectrum was?
It's not one of these. It was a different slide. It's all right. Never mind. I'll bug him later.
Another question. Is there some explanation why the addition of indium can increase the pairwise selectivity for the rhodium catalyst?
So yes, like I described here, because with more indium you incorporate it onto the rhodium surface, you can increase the diffusion barrier of hydrogen diffusion on the surface. So if the diffusion is inhibited, that there is a greater chance for the hydrogen to add onto the carbon double bond in a pairwise fashion, which is a key element to observe the hydropower signal.
So I guess I have a follow-up kind of question off of that as well, which is, I guess if you increased the ratio, would it be possible to increase the ratio any further? And then off of that, I guess, would you see this trend continue of increasing pairwise selectivity?
Yes, that is possible, but it's just we need to consider like the easiest way for the intermetallic phase to form, because with more inert metal in there, the formation energy of the intermetallic phase may be even higher. That makes the phase more unstable.
Okay.
Yes.
And then one more question from the Q&A. Are there potentially other advantageous surface structures to study with other metals, platinum or palladium or anything else?
So far we see that the rhodium catalyst is like one of the best catalysts for such a study. We're still exploring other metal compositions. So yeah, it is possible that we could find another like a better composition.
Why did you choose indium as your inert metal for this study?
So actually, in theory, that as long as it is inert metal, it should like have the similar effect. It's just I think the indium is one of the easiest one to incorporate onto the rhodium surface as far as the synthesis.